אורין, כמה זמן בשיעור? דקה.
שנייה אתה רוצה?
בזמן.
59.
איפה קבית?
הם יעבירו אליה. הנה, אתה יכול להתחיל.
מתחילים?
כן.
We are on air? אנחנו באוויר?
כן.
Good. So hi all, we are on air. It is happening, right? Come on, this is a miracle, right? We make history. שנגיד שהחיינו, but we'll get to that maybe in the toast at the group photograph later on. So as you can see, we are in a real-time experiment of hybrid conferencing. There are 200 people attending physically here in Haifa, while there are many others joining remotely around the world through YouTube and other platforms. And this includes Kavita, our program chair. She couldn't come here due to the situation, but would have loved to come, but I believe we'll soon see her here. We are not aware of a hybrid conference, a post-COVID hybrid conference at this scale in our field, except for the Oscars. Okay? And as an experiment, we actually expect it will not be unexpected if we screw up today and have some faults, so we appreciate your trust and patience. Throughout the day, you will receive information about what is ICCP, the processes for accepting work, for presentation and publications, awards, and how to participate remotely tomorrow and the day after tomorrow. That will be through GatherTown, and you'll get instructions about this. Meanwhile, here are a few urgent points for those who are here in Haifa. So please to help us control the COVID situation, remain in the hotel area, which is destined for our activity, which is the lobby, this auditorium, the 2 dining halls, and of course the promenade by the beach. Wear masks indoors, outdoors, of course, you don't need to, I think. And keep a distance. Arrive on time to the group photo, and to the lunch, after the lunch, come back here for the session, because as I remind you, we are live internationally and we want to be on time. And we have several student volunteers here. They have white shirts, and you can see them around. So if you need assistance, finding a seat, getting a microphone, etc., just reach out to them. And it's an opportunity to thank them, to thank the volunteers. Thank them. And mentioning volunteers, we need to thank not only these students. Okay, so we need not to thank these students, but the whole local arrangements team, which include Tomer Michaeli, Yoav Shechtman, not to be confused with me, okay? And Meital and Anna and Anat Levin. So thank you for the local arrangements for helping getting this up.
Behind all of us is an amazing international organization team who worked in a very complicated year on a very complicated hybrid operation. Their names are here. We want to specifically highlight young researchers who, while writing papers, writing grants, worked day and night for months to get us here. They did everything behind the scenes. They worked super hard. We are so grateful to them. Thank you. The youngest and busiest are Yelena and Judith, who are there. Raise your hand. Thanks. Who built and update constantly a wonderful ICCP website, who is still updated as we speak. They are master students at Tali's lab. Kudos. They want to keep us connected to the world in real time now as we speak. In this broadcast and in virtual conferencing are Yanis, Aditya, and Yoav Shechtman. Thank you very much.
Yoav is here.
Yoav is here. Let us hope for their success today. And Vivek, Matt, Gordon, and Suren, who worked to get our papers published, formalize poster sessions, and obtain the funding.
Is Kavita here?
Now we switch to Kavita, who is with us online. Let's see if we can see her.
Yes.
It's our first test for the
Can you hear me?
hybrid
Hey,
event.
Kavita.
Kavita.
Can you hear me?
Just a second, we cannot
Yes.
hear you. You know, there's this sentence, you're on mute? No, you're not
Hi.
on mute. Okay. Okay, Kavita, to you.
No, we didn't hear her.
I'm speaking. Can you hear me?
Yes.
Yes, we can hear you.
No.
Yes, we hear you. We hear you, Kavita.
Kavita, we can hear you very
Okay.
well.
All right. So we want to thank the whole program committee. We want to thank the whole program committee. Okay, I'm going to start. There's a lag, so there's a lag.
Yes, there's a lag, but we hear you very well.
Yeah, keep on moving.
All right. We want to thank the whole program committee, optics board, and the steering committee for defining a great program and providing valuable advice.
Wait a minute, Kavita. Is there any way to control the lag or something? Okay.
This is a difficult time with COVID and heavy workloads in that time. People were reliable and thoughtful in the work they did.
Kavita, maybe you don't want to hear what you're saying, so you don't notice the lag.
Kavita, we hear you very well. You don't have to stop.
Don't stop. We hear you
We
very
want
well.
to thank our sponsors who supported us in this year. Okay. All right. I'm just going to go ahead. Okay. So we thank our sponsors who supported us in this difficult year. We specifically thank the Technion for direct help, the IEEE Computer Society for being very flexible, and actually we in ICCP here today serve as a case study for IEEE on creating a hybrid post-COVID conference. We hope that this will be an interesting model for the future.
Okay. Kavita, shall we move on? Shall I take over?
Finally, I want to say from Ori and me, who are co-chairs, you have really pushed to make this exciting hybrid event and many of the changes. So I want to especially thank Yoav for his hard work. And Yoav, you should take over.
Okay.
Thank you, Kavita.
Okay, thank you, Kavita. So now let us move to the first session. It will be chaired by Tali Treibitz. And it is symbolic that Tali Treibitz is chairing this session because Tali Treibitz presented a paper in the very first ICCP. This is the 13th ICCP, so she presented in 2009 as a student, a paper in ICCP. Welcome, Tali.
Thanks, Yoav. Yeah, so I remember the first ICCP in San Francisco, and I'm really happy we made it to this side of the world. It almost didn't happen, but thanks again for all the efforts. So, yeah. I'll be chairing this session. We have two very exciting keynotes, and we'll start on time, right? And for the YouTube audience, I'll be monitoring the chat below in the YouTube channel. So when you have questions, you can type them, and I'll transfer them to the speakers. So the first speaker is Dan Oron. Dan Oron earned his BSc in Mathematics and Physics from the Hebrew University. Should I say the year, or should I skip the year? Then a master's degree in physics on hydrodynamic instability from Ben-Gurion University of the Negev, and then a PhD in physics from the Weizmann Institute of Science. Then he returned to the Hebrew University for postgraduate research with Professor Uri Banin, and later went back to Weizmann and joined his faculty in 2007. This is he's currently a professor at the Department of Molecular Chemistry and Material Science at the Weizmann Institute. His main research interests are at the interface between light and the nanoscale. And I'm very excited to hear this talk because I heard there will be marine organisms involved. So this is a topic close to my heart. And welcome, Dan. Thanks.
So thank you, Tali. Thank you, Yoav, and Ori and Kavita for the invitation. And thank you all for being here. It's amazing after this year to speak in front of real people, not black boxes with names. And so I'm excited, having not done this, for a while. So today I'm going to talk about inspiration, and I think we don't really often appreciate the inspiration that we can get from nature. And this talk will revolve about the kind of inspiration that we see mostly in the visual systems, in the color systems of marine organisms. And the title is the Nano-Optics of Life, because we try to connect nanostructure, self-assembly materials at the nanoscale with what we actually see. So without further ado, let's start. So as mentioned in the introduction, my group does a lot of things. We do semiconductor nanostructures, we do photovoltaics, we do things that are more in the sort of topics that are covered by this conference, like imaging and endoscopy and lensless imaging and phase retrieval. But this time I'll talk about something else. If you want to learn about our microscopy work, you could check that out in the poster session. So optics appears in many contexts in biology. Most importantly, vision, but also communication, camouflage, photosynthesis, you name it. It's, for us, definitely the number one sense. So we use light all the time. But actually in the animal kingdom and in the communication between plants and animals, it's ever present, right? And evolution has pushed forward so much development that I want to share sort of a bit of that and a bit of the awe that I have when looking at biological systems. And these are images of all kinds of systems that we've studied and we might see after this talk. So if there's a sort of a message that I want to convey here, is that it really is worthwhile studying natural biological systems. And the way we came to it is to try to combine structure and spectroscopy in order to sort of understand function, which is not always easy in biological systems, and then perhaps learn something about applications. And we basically try to reverse engineer a system which has evolved over many years. And reverse engineering is always hard, and reverse engineering with evolution is especially hard because evolution is a one-time experiment, right? So we know that what evolved served for some fitness goal, probably at some point, although some things were sort of, I guess, accidental. It's definitely not always an optimal solution, but definitely an interesting one. And so if there's sort of three messages that I would like to convey in this talk is, first, natural systems are amazing, worthwhile looking at. The second is this approach of combining structure and spectroscopy helps us to understand function. And the third is that sometimes, if we're lucky, and I'll get to that sort of towards the end of the talk, we can learn something that we actually didn't know from nature. Although almost all that we know in optics, nature discovered long before us. So let me start just with an inspiring example or a movie, which is the unique optics of the Copelia mirabilis. So Copelia mirabilis is a copepod, sort of, something at the bottom of the food chain. This is a Copelia mirabilis. It's about 1 millimeter in size. It's, as I said, at the bottom of the food chain. It's called a sea sapphire, in sort of what divers would call them. And this Copelia here is always in the frame, right? Sometimes you see it, sometimes you don't, and it plays this disappearance act, but it's always there. And this particular one was filmed by a diver, a person running a diving school in Indonesia, and was kind enough to allow us to use his movie in a paper. And you look at that, and that's sort of amazing, because you see a mirror, a perfect dielectric mirror, right? There's no metals here. This is completely transparent when you look at it, but then every once in a while it looks just like a perfect mirror. So I'll show you something about what this is and why this happens soon, before going to a bit more complex optical systems, which are sort of more in the context of this particular conference. So reflections are all around us, right? We see reflections everywhere. They're not always of the same physical origin. So reflections can be from a metallic surface like the mirror. Some of us prefer not to look at in the morning. Or they can be from a dielectric interface, like a single reflection from a grazing incidence from a lake or the beach if the sea is really flat, or from a gradient of refractive index like a Fata Morgana, mirage, right? There's no interface there, it's just a gradient of a refractive index. Or it could just be the Fresnel reflection from an interface between two dielectrics where one region is particularly dark, and so you don't see light from inside this store, you just see the reflection of the outside. But it's ubiquitous, also in nature, right? And from a physics point of view, it all boils down to one quantity. It's the refractive index. So the refractive index is the really important quantity, and connects the speed of light in a medium to the speed of light in vacuum, and also the attenuation in the medium if there's absorption, and also the polarization of light, because light is a transverse, not a longitudinal wave. And the theory of this was developed by Jean-Augustin Fresnel a long time ago. And we know of two kinds of reflections. One at the dielectric metal interface, that's like a metal mirror that we often look at. The more common in biology is a dielectric interface, right? Metals are not very common in biology. And we're going to focus on this very, very small section of the electromagnetic spectrum that we for some reason enjoy. It's the visible light. And if you want to interact with visible light, you need structures which are submicron. Hence, it's interesting to talk about nano optics. So let's look at a few examples. So what is like the most common dielectric reflector that you've always seen a zillion times but never thought of? It's something that's very, very common, right? You see that everywhere in the animal kingdom, but very rarely do you see it in artificial systems. So if you want to construct a reflector from just dielectric materials, this is sort of the way to go at it. You build something which is called a quarter wave stack. What is a quarter wave stack? It's a stack of high-low index materials where you make sure that every reflection here, so from every two interfaces, you have a Fresnel reflection. It's a small percent of the light that's reflected, but you make sure that the interference between all these backscattered waves is constructive. So eventually you get significant intensity in the backscatter direction. And it doesn't take a very complicated use of the Fresnel equations to understand that the perfect sort of stack is something called a quarter wave stack. What is a quarter wave stack? Every layer, so it's first a high-low index, and every layer has an optical thickness which is exactly 1/4 of a wave. And then all the back reflected waves interfere constructively. And this is, if you buy a dielectric mirror, this is what you get. And there's basically two parameters that control this. One is the number of layers, the other is the index contrast. What is the ratio of the high index to the low index? And this follows this formula here. So as the index contrast increases, you need less and less layers. But of course, this is something that if you buy a dielectric mirror from a manufacturer, there are many of those, they would usually be quarter wave stacks. But nature doesn't have to actually obey our design rules. And I'll show you an example to that soon. And then you can generalize this idea of a dielectric reflector to higher dimensions. This is called photonic crystals. Photonic crystals were pioneered by Eli Ablanovich about 30 years ago. And it's basically a generalization of this idea, right? You make sure that all the reflections interfere, but in several dimensions, 2 or 3 dimensions, you can basically make a material system that does not allow light to propagate inside it. You can think of a dielectric mirror as one that in certain directions does not allow light to propagate in. It's rejected, right? It's backscattered. But you can make a 3D system that light from every direction will be rejected, will be backscattered. And that's a three-dimensional photonic crystals. This is a picture of the first three-dimensional photonic crystal. And for that, you need a high index contrast. You need an index contrast with current designs of about 2 in order to get a full band gap, a material that just rejects a certain wavelength from every instance. Okay, so I promised biology. What is the simplest dielectric reflector that you've all seen and never thought of? You've all gone to the fish market, you've all bought fish, you've all looked at fish scales. I don't think that many of you have ever thought what's inside there that makes the silvery reflectance. So the silvery reflectance of fish, the purpose of that is sort of simple, right? It's camouflage. You can sort of get that because from the bottom, you know, the fish look reflective. From the top, they look typically dark, and that makes sense. It's just like a fighter plane that you paint, you know, blue from the bottom and sort of dark from the top, so that when you look at it from the bottom, it resembles the sky. When you look at it from the top, it resembles the earth. But what's in there? I mean, these are quite good mirrors. They reflect nicely. And if you look inside a fish scale, you find that in the scales you have these special cells called iridophores. And inside each iridophore, you find this is cryo-SCM, so freeze-fractured material, so that water is vitrified, and you can actually look at the structure, and you see these crevices, and each of these crevices contains a single crystal, those sort of hexagonal-shaped crystals, and there's many, many, many of those. And it's a funny stack of high-low index material. So the first question is, what is this material? Right? And the material is the material of choice for biological reflectors in the marine kingdom, also for some animals above ground. The material is anhydrous guanine. Guanine is the same material that we know from our DNA, one of the nucleic acids. It's a very simple molecule. It crystallizes in this manner. So it generates planes which are hydrogen bonded and weakly bonded in between planes. And this very, very anisotropic structure leads to a very, very anisotropic refractive index. It has a refractive index of 1.83, which is quite high, well above glass, in plane, and only 1.45, which is below glass, not very far from water, or protein, water, cytoplasm, water which contains protein in the orthogonal direction. So why guanine? First, it has this high index, much higher than other materials used in biological reflectors like chitin or cellulose. And also there's cellular availability, right? Guanine is in our DNA, and the whole machinery of metabolites of DNA makes it actually a waste product, which eventually is ejected by urinating. And so it makes a lot of sense to use it because there's high availability of this material. But the refractive index is really high, which means it makes sense. So if you look at a fish scale, you would say, okay, makes sense, this is a quarter wave stack. That's what people who first studied fish scales thought, but turns out it's not a quarter wave stack. The plates are really thin. They're about a 16th of a wave, not a quarter of a wave. And the distances are sort of weird. Now, people, when they saw that, they thought this is what we call an Anderson reflector. Any arrangement of random scatterers eventually backscatters everything, sort of like white paint. But actually it's not random, because if it were a random reflector, fish scales would have a bluish hue. They would reflect more in the blue than in the red. So when you look at that you can do only with cryo-SEM or methods that do preserve distances. you learn that there's short-range order, but not long-range order. And this sort of balances out the colors, so you get a silvery reflectance. So there's even thought put into ordering the layers. But that's sort of a simple reflector, right? What about, quarter wave stacks? So for quarter wave stacks, let's look at one of those copepods. This is not Copelia mirabilis from the movie. It's a copepod called Sapphirina metallina. And here you see perfect periodicity, right? Beautiful perfect periodicity in the cryo-EM image. And you see a really nice color. This is not silvery. And this makes sense, right? Because in a quarter wave stack, it's a quarter wave for a certain wavelength. And if you take the distances that you measure from the cryo-EM, right, you can calculate the statistics of the variance of the distances, the variance of the thicknesses of the layers. You can simulate what is the reflectance of this particular copepod based on the structure, and you get the top curve there. And then you can measure the reflectance of the same animal before you freeze fracture it, that you get the bottom curve. And you see perfect agreement between these two. And this is really very, very close to a quarter wave stack. And then you can look at how this quarter wave stack looks. And it's just mind-boggling. So this Sapphirina metallina, as you can see, is about 1 millimeter by 0.5 millimeter. It has on its back, a layer which contains 20 million identical hexagons like that. Each is made of single crystal guanine. It has a dimension of about 1.5 microns, but 20 million identical ones, so they're tiled. And they're tiled in layers like that. So you see 12 to 14 layers of identical tiles, one on top of the other, perfectly aligned with each other. All of them have the same crystalline axis. So the high index in plane means that light from above, which is the light you want to reflect, sees only the high index, doesn't see the low index. And this is just an amazing system. It's all self-assembled. I don't know how anyone could make such uniform crystals of any material, and I don't know how one could arrange this. But this is really a wonder of nature. And when you look at sea sapphires, they come in many flavors and colors. They're all perfect. And you could ask yourself, what is this? How come that they have different colors? Is it like the colors of our hair, that different people are born with different colors of hair because genetically, or is it something dynamic? And then you could also ask, why these colors? So sort of why these colors, the question is easy. Only the males have colors. In certain types of sea sapphires, only the females have eyes. So I would, it's not a hard guess what is the purpose. But then, okay, why? You want to communicate, right? This is like a peacock. You want to show the females the color, but if you're at different depths in the ocean, you want to have a different color, right? Because the light well below the surface is only blue, close to the surface it's green. And so we had this idea that the structure likely is something tunable. And I want to show you this time-lapse movie of a single Copelia mirabilis, dark adapted, so it's blue, and then we put it in room light for a while, and you see that over time it turns golden, right? So as it adapts to light, it turns golden. This is completely reversible. And the reason is that when they go up in the water column, right, when they see more light, they want to reflect more light. But as they go up, so well below the surface, you want to be blue. And close to the surface, if you want to be seen, you have to be green or golden, because light is yellow close to the surface, and blue deep when you don't have light. This is the Copelia mirabilis that I showed you before, and it has a different mechanism or a different effect, right? Deep underwater, it is blue. Then when it goes to the surface, it doesn't want to be seen, doesn't want to be eaten. It becomes completely transparent. So this guy's alive, right? You can see it moving, but the sort of the color oozes out, fades out completely. And the mechanism here is by basically taking this stack and it's crystals which have which sandwich a water layer or a cytoplasm layer. They're basically pumping water or cytoplasm in and out of these cells. So it's a tunable mirror. They can change their color by just pumping fluid in and out of this optical element, which is mind-boggling because we can't do this. We don't know how to do this. There are alternative colors, for example, alternative mechanisms for changing colors. For example, this neon tetra fish knows how to change its stripe from blue to green, and it does it in a different mechanism. Instead of pumping water in and out, it introduces strain between the layers, basically tilting the crystals. When you tilt the crystals, you change the effective distance. That's the Venetian blind kind of mechanism that I show on the left. But this is all just a prelude. I promised you something on visual systems. So is this systems of reflectors, made of guanine and related materials unique? The answer is no. And the most prevalent place that you can see this in underwater marine animals is in the visual systems. And seeing underwater is a real problem. So for us, we have eyes that are more or less round, spherical, and the refractive index inside the eye is about 1.5. Outside, it's about 1. And that makes things really easy for us. Because if you take a sphere with a refractive index of 1.5, you use the refraction from the front surface, you get focusing on the back surface of the sphere. And that's for an index contrast of 1.5. But underwater, the index contrast is much lower. It's outside, it's water. It's 1.33. Inside, it's still 1.5. And so marine animals had to develop mechanisms for vision, for actually seeing acutely, which are very, very different from what we use above ground. And some examples that I'll show you are, first, mirror eyes, like the ones of the scallop. So the scallop doesn't have an effective lens at all. The way it sees is that the back of the eye here is a mirror, a dielectric mirror. Each scallop, by the way, has hundreds of eyes. You can see them over there, those small blue objects. And the back of the eye is a mirror. So light actually goes through the retina. Here it is backscattered onto the retina from the mirror. The mirror is also made of guanine. Now of guanine squares, exactly identical to one another, about 1 micron in size. And scallops have 2 retinas. That was a riddle for a long time. Why do scallops have 2 retinas and not 1? This is the proximal retina here, and this is the distal retina here. And if you run simulations and study, freeze-fractured eyes, you can actually start looking at the geometry. And scallops developed this way of overcoming the tremendous aberrations of reflective optics by using 2, not 1, curved detectors, right? So we use a planar detector in our cameras. They use 2 different curved detectors, one which is very efficient for the central vision, the other is very efficient for the peripheral vision. So that makes a lot of sense, right? You use the very distorted geometry of the detector, of the retina, in order to overcome the huge aberrations by your mirror eye. And of course, the spectrum of the reflection here nicely fits the light insulation that you have in the habitat, the natural habitat of these scallops. This is another example. You can look at the zebrafish eye or any fish eye. They don't have absorptive irises like us. They have reflective irises. So the iris here is reflective. Why do fish have reflective irises, not absorptive irises? And this iris is a mastery of design. It has an ordered mirror-like layer and then a disordered scattering layer and then a very thin pigmented absorbing layer. And that's sort of a funny riddle. Why do they use all this? Why do they need to construct all this structure? And the answer to that, or at least what we think is the answer, is that they need to see well when they're very young. And when they're very young, at the larval stage, the whole eyeball is about 200 microns. And so you have to reflect light. You have to reject light from the iris with very, very thin irises. Right? You can't afford to have a 70 or 100 micron thick iris like ourselves. Like mammals, which enjoy growth in dark conditions in the womb, and then go out to the world when their eyes are already well developed. So 7 days post-fertilization, they already have a rather effective iris, but it's extremely thin. It's less than 10 microns. And so zebrafish have learned that at very small dimensions, if you're limited in space, reflective optics is much, much better at rejecting light than absorptive optics. Of course, if you're unlimited in space, an exponent, which is absorption, always wins versus a power law. But for very small dimensions, this is not the case. And now I'll show you a third, last example of a reflective eye. This is another engineering mastery. This is the superposition eye of shrimps. It's also an eye that's based completely on reflection. And it's constructed this way. This is the retina and the rhabdoms. These are the photosensitive elements. But there's no effective lens. Light from infinity is reflected by a thin layer of mirrors here, the distal mirrors. And now, if you think of light coming from infinity, it's reflected from each mirror. Now, because each of these mirrors has a different orientation, this is on radii, then they all reflect light into the same rhabdom. But now, because these rhabdoms are big, tens of microns, they scatter light, you have to somehow ensure that there's no scattering of light within the retina, because scattering of light within the retina would blur vision. Also would induce loss in the detection. And then there's this tapetum reflector, which looks like an egg tray, which basically prevents light arriving at one rhabdom to reach the other rhabdoms, and also increases the efficiency because it's a very highly reflective structure. But now, you need to make this, if you want your fill factor, think of this retina as a camera. If you want the fill factor of the camera to be high, you need to have this tapetum reflector very thin. So you need to make a very thin, highly efficient reflector. So first, this is sort of the structure. And if you look at it using CT, micro CT, you see this white material here. This is the optically relevant material. It's not guanine. It's a close cousin of guanine called isoxanthopterin. And it appears both here and here. This has a higher refractive index than guanine. Very similar structure. In-plane refractive index above 1.9. And this is the tapetum reflector. So you can have a look from the side or from the top. These black holes are the pigment where the rhabdoms are, the photosensitive elements. And all this whitish encasing, that's the scattering layer. So you can also appreciate the fill factor, which is quite high because the top of the rhabdom here is narrower, but it's also encompassed in this material. And now if you look at the tapetum reflector from up close, you see that it's made of these small spheres of like a sphere pool that kids play in of this material, isoxanthopterin. And looking even closer onto it, you see that these small spheres, each is about 200-300 nanometers in size, actually resembles a soccer ball, right? It looks like it's made of small crystalline plates. And indeed, each of these is completely crystalline. It's made of crystals which are constructed like a soccer ball, and that means that it has this very funny shape of a spherulite. It's a material that has a different refractive index tangential to the surface and along the radial direction. So it has a very high refractive index along the tangential direction, but a very low refractive index along the radial direction. So it's something highly birefringent but spherically symmetric. And it's funny because we haven't seen this kind of structure anywhere before. Not in man-made structures, not at these range of sizes, and not anywhere else in natural systems. So we really wondered why this kind of structure is constructed like that. And then you run the simulations on it, and you see that this kind of particle backscatters light more than twice more efficiently than a similar structure made from a non-birefringent uniform material. And so, although it doesn't scatter more light, it backscatters light more efficiently. You can measure the refractive properties of these single spheres. That's how they look in electron microscopy. You can actually see that the refractive index of the real structure is well above 1.8, very close to 1.9. So biology actually, does what we think it does from the point of view of calculation. And if you look at measure the scattering properties, you see that it's almost a perfect blue reflector, which is what we both see in simulations, much better than any kind of blue reflector that we might have imagined. So this kind of structure is a unique photonic crystal. It's a very funny photonic crystal that we haven't seen before in man-made systems, made of these spherically symmetric, highly birefringent structures. And if you calculate the optical properties of this kind of photonic crystal, you see that unlike photonic crystals, which are made from isotropic materials, like all the man-made photonic crystals, it has new kinds of stop gaps, or new kind of partial gaps, new kinds of regions where no light can penetrate the structure, which makes it a much, much more efficient backscatterer than any kind of structure that we've seen which is man-made. And this sort of structure can lead to almost 100% reflection for a 6-micron layer. So imagine, it's like white paint, but if you have, say, a wall that is painted black, you want to paint it white, you need at least 200 microns of paint in order to make it sufficiently white that you don't see the black behind. But shrimps have somehow evolved these kinds of funny structures with funny materials that they can do that in 6 microns, not 200 microns. So, let me summarize. Again, as I said, the whole point of this talk is inspiration, right? I want to draw inspiration from biological systems. And I think they do exhibit such rich phenomena and follow design principles that we have independently invented or that we have not yet discovered, which is amazing. And also that the organic materials, especially organic crystals, possess really unique properties that we are not used to, like 30% birefringence, one index of refraction being that of water, the other being higher than lead glasses that we use in the expensive glasses. And also that self-assembly is an extremely potent tool for making devices that are so accurate. Like, you can't imagine self-assembling 20 million hexagons, identical hexagons of a material, into a mirror which is, real life sized. You assemble 20 million hexagons each 1 micron, 20 million tiles in perfect order, and they make a life-sized, 1 millimeter scale mirror. And then finally, studying these systems with some humility has great promise towards new designs. And before I finish, I just want to acknowledge the very long list of people that have contributed to this, so a long list of really excellent students. Ben is here. And also collaborators, especially Leah Adadi and Steve Weiner, without whom this would not have happened. And I would be happy to take questions.
Okay, because of the live broadcasting restrictions, I'll be here. Thank you, Dan. This was really exciting. So we have time for a few questions from the audience. We have a mic here. If you want to be seen on camera while asking, then step and come to this table. If not, the mic can come to you. And also, people on our online broadcasting, I remind you that you can ask questions in the YouTube channel. So I invite you to be the first one, because on the asking a question on the YouTube channel, because we don't have any yet. Okay, audience, any questions? Yeah. Can you, wait a second, אתה יכול להביא לו את המיקרופון?
Hi, thank you for the talk. I wanted to ask, how is this reflective element working? How is the reflective camera working? That is, didn't get.
So which reflective camera? I showed two.
Okay, one of them. I didn't get the concept. That's the point.
Okay. The first reflective camera, that of the scallop, just works just like a reflective telescope, right? It's just a concave mirror, which, on axis at least, can reflect all the rays of light into one point. The problem with reflective cameras, as we know from telescopes have a very small field of view. Reflective cameras have terrible off-axis aberrations. And for that reason, we don't use reflective optics for cameras that much. But then aberrations are not a problem if you can use a focal plane that is not a plane, right? If you place your detector not on a plane, but rather on a curved surface, it's like using an asphere. So you can work with at least for spherical aberrations, which are terrible. With reflective optics, you can overcome those. You can't completely overcome coma and others, hence the scallop uses two retinas. So it has two surfaces for detectors, and the joint signal from both of them gives a decent field of view and a decent accuracy of the vision, acuteness of the vision. The other camera is much more complicated, right? Rays are reflected here by an array of mirrors. The way you can think of this is if you have a point source and you want to focus light to another point, you could just use an array of parallel mirrors such that every ray would go from one point to one point. But now you can curve this so the mirrors are not parallel, they're on on sort of the radii of a sphere, and then light from infinity would focus down to a point. The beauty of this system is that it's symmetric, and so you can cover a wide field of view. Other parts of this that I didn't talk about is the fact that if you are able to control the properties of the mirror as well as shrimps can do, you can actually define the angle which is efficiently reflected to minimize aberrations while collecting a sufficient amount of light. And that's where shrimps use birefringence. They use the fact that the refractive index is very high in certain planes, but very low in the other planes, so that at some angle you get very low reflectivities already. But that's, beyond this talk.
Thanks. More questions from the audience? Yeah, Hagit.
First of all, thank you for a fascinating talk and lots of insights into this natural world. I was wondering, you sort of answered this at the end a little bit, but what are the challenges, what are the problems in taking this technology, natural technology, and bringing it into the real world? You did mention small sizes, but we make chips with very small sizes. So what other challenges are there?
So that's an excellent question, because it's something we're actually working on. These materials, first, these are organic materials, and in many of these applications they actually use the birefringence, and these materials are more birefringent than much more birefringent than any inorganic material we know. So the most birefringent inorganic material that we work with is calcite, which is 10% birefringent. These materials are 30 and more percent birefringent. And so you have to work with organics. And organics, it's very hard to crystallize them correctly. Biology typically uses a polymorph for the crystals, which is not the one that's easy to crystallize in the lab. This is the beta polymorph. When you try to just create these crystals in vitro, you get the alpha polymorph, which is different, has different optical properties. And also these crystals are very brittle, so hard to work with. So technologically, there's a long way that we have to go to get to the level. We don't even know how to grow simple guanine plates or small spherulites. So in terms of the chemistry, animals are way ages beyond us. And I think that's a major challenge here.
We have time for a last short question.
Thank you for a fabulous talk. You mentioned the spheres at the end with a refractive index of 1.9 approximately. I'm just curious, how did you measure that?
It's not easy to measure because these are nanometric spheres, and we don't have many of those because we have to extract them in a very tedious process from the eyes of shrimps. To make a long story short, we do single particle scatterometry. We combine that correlative with TEM, so we know the geometry very well. And then we fit scattering results to a model, and we can get quite accurate, I would say plus minus 0.02 estimates on the refractive index.
Thanks.
Thanks. So actually I have more questions, but I'll catch you later because we have another fascinating talk ahead of us. Who is switching the slides? So let's thank Dan Oron again. And so far, the only comment on the YouTube channel was that it was an amazing talk. So I agree with that. So while we are setting up, I'll introduce the next speaker, Dani Lischinski. Do you need that? Yeah. Dani is a professor at the School of Computer Science and Engineering at the Hebrew University of Jerusalem. He received his PhD from Cornell University and was a postdoctoral researcher at the University of Washington. In 2002, he spent, and listen to that piece of information I didn't know, he spent a sabbatical year at Pixar Animation Studios. So I don't know if you mentioned that in the talk, but we'll be happy to hear about them as well. And he also, in 2012, received the Eurographics Outstanding Technical Contributions Award. His areas of interest span a wide variety of topics in the fields of computer graphics, image and video processing, and computer vision. And we'll now hear about controllable generative models, the end of stock photography. So thanks, Dani, and please use the mic, okay?
Okay. Thank you for the kind introduction, Tali. And huge thanks to all the organizers who came up with the truly revolutionary concept of actually gathering people in the same room physically. It's very innovative. And good morning, everyone. Thanks for coming. I'm very honored to be here. So the topic of my talk is this change that has happened in our field, which is computer graphics, computer vision. I mean, at least myself and most of my colleagues have experienced this change, and our research agendas have changed drastically. And the change I'm talking about, of course, is the change that is due to the emergence of the deep neural networks and their phenomenal success in various tasks in computer graphics and computer vision, especially of particular importance to people like me who grew up in computer graphics, which is all about synthesizing things, synthesizing models, synthesizing images. So of particular importance to us is the emergence of the various generative models, the neural generative models that are capable of just incredible things today, things we didn't believe would be possible in such a short time as it took for them to develop. So in my talk today, I'll start with a very brief personal perspective, what drew me to generative models, and then I will proceed to share with you just a few of my recent research projects, which all of them happen to use extensively generative adversarial networks, or GANs, for controlling and manipulating synthesized images. Okay. So, where's my mouse? Okay. So, I've been doing computer graphics since around 1988, so I'm that old. And I became fascinated with computer graphics after learning about the ray tracing algorithm in an introductory computer graphics course that I took at the Hebrew University. And then I ended up doing my master's thesis on ray tracing. And that's actually this pink teapot that you see here. That's one of my first successfully ray traced images. And then I liked photorealistic image synthesis so much that I decided to pursue my PhD degree at Cornell University, which was the place at the time for photorealistic image synthesis. They were doing lots of global illumination research and radiosity research, and indeed my PhD was about radiosity, and that image on the right is one of the images from my PhD thesis. And in fact, my advisor at Cornell, Don Greenberg, he was a big believer in photorealism, and in fact we used to joke among the students that he started all of his papers with the same phrase, which was photorealistic image synthesis is the holy grail of computer graphics. And then of course we, the students, would have to remove this sentence so that not all papers start the same way. Anyhow, already back then we were painfully aware of the fact that just regular ordinary image metrics are not able to capture realism. They're not able to tell us how realistic an image is, or how close it is to a realistic image. And we were fantasizing about some kind of a perceptual error metric, or a photorealism oracle, if you like, that would help us determine how realistic an image is and what can be done in order to improve its realism. So, if this sounds familiar, that's because it turns out that back then, 25 years or so before generative adversarial networks, what we were talking about is a discriminator for realistic image synthesis, right? Oh, by the way, let's see a show of hands. Who thinks the, who thinks the image on the left is real versus the image on the right is real? So, which image do you think is real? Anyone? Okay, we see some disagreement. Okay, none of them is real. Okay, they're both, one is a work by an artist, another one is just a rendering by computer graphics. Okay. So once again, it's really not a surprise that 20-something years later, when I first heard about generative adversarial networks, I was really excited, and I was not the only one to get so excited about it. Famous people like Ian LeCun proclaimed this to be, the most interesting idea in machine learning in the last decade, and since then, there were an incredible amount of follow-up works. I think in Google Scholar, the number of citations to the original GAN paper at the moment stands above 30,000, and this plot just shows the number of papers that actually talk about GANs, not just reference that paper. And indeed, one of the major applications of generative adversarial networks, or GANs, is synthesizing images that look like they're completely real. On this slide, you can see the evolution, the progress of GANs over the last, over the first 4.5 years since their introduction. So you see the type of faces that the original GAN paper was able to generate, and the last one from 2018 is the one generated by StyleGAN. So unlike the biological evolution that was featured in the last talk, the evolution of neural networks is very, very fast. And they're good not only at generating human images, but other image classes as well. So for example, these are some of the images that are generated by the big GAN architecture, and that's a big GAN model which is trained on the entire ImageNet data set. And I've already mentioned the StyleGAN architecture, which is my favorite, as you'll see later in the talk. And because I believe it's the one that brings us the closest at the moment to this holy grail of photorealistic image synthesis. So one might argue that just generating random images using some random vector, which is what the standard GAN is doing, isn't the most useful task for computer graphics. But nowadays, we also have many flavors of GANs, and very popular are the conditional generative models, or the CGANs, where the output image is controlled by various input conditions, which could be, for example, another image. So, for example, this other image could be a satellite image, and then the GAN could generate something that looks like a Google map out of that input. Or one might provide the GAN with a sketch, and the GAN would generate a photorealistic image of a handbag. So this task in general has been known, people refer to it as image-to-image translation, and the first project I would like to tell you about is about that. Before that, let me just mention that in this area of image-to-image translation, particularly popular, a particular popularity was gained by this idea called the cycle GAN, where we can train a generative adversarial network, actually a pair of them, to translate between two image domains without ever specifying explicitly that certain images in the first domain correspond to other images in the second domain. So it's an unpaired image-to-image translation task. For example, all you need is to assemble a training data set of, say, horses and another data set of zebras, and then you can train two generative models, one translating zebras to horses, the other translating horses to zebras, and they train in unison to achieve this task. And you can get lots of interesting image manipulations in this manner. However, image translation does not work very well when the image structure is changing. So the reason that it works so well when translating zebras to horses is because most of us are not zoologists, and we cannot say, hey, that's not a horse, that's just a zebra that looks like it's been painted in brown color, right? Because there are actually geometric differences. I mean, the shape of the zebra and the horse is not exactly the same, but for the most of us, it's close enough. So we look at this image, we say, oh, that's a great result. Or similarly, when we translate a winter scene to a summer scene, we cannot really tell how good this translation is. And all it involves is really just changing the colors and the textures of the surfaces. It doesn't really change any of the shapes. So what happens if you try to take this concept like cycle gun-like architecture and you apply that to a pair of domains where there is a significant geometric difference between the two? For example, what happens when you try to translate zebras to giraffes rather than horses? Now, anybody on the street can tell the difference between a giraffe and a horse and a zebra, right? So these are some of the results that are achieved by that were achieved by state-of-the-art image translation methods at the time. And as you can see, you can hardly think those are successful results. Similarly, another example is attempting to translate elephants to zebras. Okay, so we wanted to address this task, and in a nutshell, our idea was that translating directly in the image domain, pixels to pixels, is not the right way to go. Rather, we can use another neural network that was actually pre-trained for classifying images, classifying natural images, like specifically we used the VGG architecture, which is also well-known architecture from around 2015 that classifies images. And these networks, they tend to extract a lot of high-level semantic information from an image. And so our reasoning is that if we do the translation on the higher semantical levels and then somehow reconstruct the image, we can get better results. So in fact, given the same setting, which is two sets of images without pairing, which is the same setting as in CycleGun, we also consider not only the images themselves, but rather the sets of their deep feature maps as extracted by a pre-trained convolutional network, the VGG. And then this is our training set, basically. Our training set consists not only of the images themselves, but of the images and their deep features. And then we work our way back from the coarsest level up to the finer levels. And for each level, we train a cycle gun, meaning a bidirectional model that transforms from one domain to the other and vice versa. And then, so we train one for the coarsest level, and then we train another one for the next level, which is also conditioned on the result of the translation in the previous level, and so forth. At some point, after 3 or 4 levels, we found that we can stop and just use this technique that's called feature inversion in order to obtain from a set of features the natural-looking image that gives rise to those features. So having trained this machinery and given an input image, what we can do is we extract the deep features from that image. We translate each deep feature to the one in the other domain using the translators that we've trained, and reconstruct a new image. And this way we can hopefully deal with translations which involve shape deformations. And here are some examples. So here's our attempt at converting a zebra to an elephant. So I think you can see some significant shape changes, and but you can see that the pose stays roughly the same, and if you have multiple instances, the same multiplicity is retained in the result. Also in this example, when the two elephants are kind of cropped off by the boundaries of the image, the two zebras that we get, they're also cropped in the same way. So it's image translation in the sense that pose and high-level semantics are preserved, but not the specific fine-grained shapes. A couple more examples. This is a challenging one because a zebra cannot really do this pose. But we kind of get the closest that the, I guess my uninformed opinion is that this is the closest a zebra can get to this point. And this is the opposite translation from zebras to giraffes. And we can also do some other translations which don't deform the shape as much, but still very different shapes, which are dogs and cats. And as you can see, it works quite well. So now, let me, as much as image-to-image translation is fun, I want to now to go back to unconditional image generation, which is, and more specifically to talk to you about the style gun architecture. So I don't know what background does anyone here have about deep neural networks, but this is like a high-level view of the style gun architecture. Basically, as most guns do, they start with some kind of random vector, but what makes it different from other guns are a few aspects. One aspect is that rather than feeding this latent vector directly to some generation pipeline, what happens first is that we have a mapping network that converts this initial latent space into an intermediate latent space, which is usually, the initial one is usually denoted by Z, and the intermediate one is usually denoted by W, right? And also there is a learned constant, and all the generation actually starts from that constant, and all the different images are actually generated as different variants of the generation process, which are controlled by a set of parameters, which are called style parameters. And there is a mechanism called ADA-in, which applies these style parameters to the different convolution layers of the generator. So all these architectural changes actually make the style gun architecture very susceptible to controlling it in semantically meaningful ways. And that's something that we've been exploring in a series of works. So in the first work, we took a look at what is this root constant that all the generation is starting from? What does it really mean? Okay, so actually, if you just take a lot of latent vectors and you average them, then and you feed the resulting style parameters to the generator, you get sort of like an average image produced by this style gun generator. And for different domains, this is what these average images look like. So basically, the constant, that's our physis, encodes in itself the mode of the learned distribution, like the average human face or an average bedroom when the model is trained on a set of bedroom images, or the average car, which has an average color, which is gray, and an average pose, at least the average pose of a car in this data set. So this raises some questions. One question is, can StyleGAN cope well with multiple modes? Like, for example, what if we have a data set that contains cats and dogs? Or, one can also consider that, maybe men and women look different enough in the human faces data set, but there is more of a continuum there. But in sets that have really two different types of content, like cats and dogs, such continuum almost doesn't exist. So one question is, how can we cope effectively with these multiple modes? And another question is, can we control the mode, like whether we get a cat or a dog, independently of whether we get a a creature with red fur or dark fur or looking left or looking right, things like that. And it turns out that the answer to both of these questions is yes. So this is already, I'm jumping ahead to one of the results from this work, which shows that we've trained a single model in which we can specify which mode we would like to obtain, and then if we specify the one mode, we get only dog images, and another mode, we get only cat images. But you can see that switching the mode does not necessarily imply that other properties are changing. As you can see, there's a lot of visual similarity in each row, in each column here, which means that the style remains constant. So how does that work? Actually, it's very simple. If we go back to the high-level view of the architecture of the style gun, remember we have this mapping function, and we have this intermediate latent space, and we have the generator, which starts from a constant. So when we want to handle multimodal data sets, all we need to do is to replace one constant with multiple constants. And we have another small network which also learns which weights each of these constants should be given. And then there's a small simple module that doesn't learn anything. It takes the weights, it combines these k constant into a single one, and then the generation proceeds as before. And this entire process can take place completely with no supervision whatsoever. The only supervision is by the hyperparameter k. We need to tell it how many modes we expect to have. Let me show the effectiveness of that with a synthetic example. So we constructed a synthetic data set which consists of these simple images. Each image has two rectangles, and the width of the rectangle is the only thing that's changing in all of these images. And the way we construct this data set is in such a manner that the distribution of the two widths is like this. I mean, we can plot it in 2D. So we design it so that it creates this letter H shape distribution. So it's a complicated distribution. I mean, it's not very complicated, but it doesn't look like a normal distribution, right? So if we train a regular style gun on this, this is the distribution that we get. And if we train our modified style gun using k equals 3, we get a much better representation of this distribution. And in fact, if we take, these are the three modes of this trained style gun. And if we take each of those three modes and fix the generation to generate only from that mode, and then we get basically the distribution just around that mode. And we can see these three distributions. You can think of them as being sort of like three basis functions from which you can more easily construct shape like that than from a single basis function. So I've already showed you the results on the cats and dog data set. Here's another example. On cars, here we used k equals 4, I believe. And in the cars example, actually we were expecting the modes to be different colors. But in fact, it turns out that the style mechanism of the style gun it's very easy for it to generate different colors. And it decided to learn that the modes should be the different car poses, okay? So basically, each row on this slide is a different pose corresponding to one of the 4 modes that our system has learned. And again, you can see that we can fix the mode and then just change the other different visual properties, like the shape of the car, the color of the car, the background, all that stuff. Or we can fix the other parameters and change just the mode, and then we get what essentially looks like the same car viewed from different directions. Okay, I mean, I'll clue you in. It's not really the same car. You can see some small differences, but it looks like the same car. Oh, here's another example for bedrooms. we had to go up to k equals 16 on bedrooms, and it turns out that the different modes with bedrooms capture what is the view angle and where in the room the bed is located. Okay. So that was that work, but it turns out that messing with the style parameters themselves can give us an even more fine-grained and a more disentangled manner of controlling the results. So this is the topic of this project that is actually, I mean, it's been accepted to CVPR, but it hasn't been presented yet, so this is the first conference on which this is being presented. So what we're trying to do here is to find controls that enable us to control the manipulation of style gun imagery in a very fine-grained and disentangled manner, meaning, for example, suppose we just want to change the shape of the hat, or just to indicate whether a hat is present on a person or not, but not to change anything else. Okay, so this is an example that you see in the top row, and again, just to remind you that we're able to do more things than just people. You have the cars in the second row, where we control only the appearance of the headlight region of the car, where everything else stays pretty much the same. Or in the third row, that's the style gun trained on the bedroom data set, where we can control the presence and the size of pillows on the bed, and actually nothing else changes. So this is called disentanglement, right? Okay, so what's happening here? Again, I have to go back to the, and every time I have a different diagram for the architecture, because the styles come from the slides come from different presentations. So again, this is our style gun architecture. Again, we have the mapping, and we have the generator, which is controlled by style parameters. And so what happens is that, did I skip something? Yeah. A slide disappeared. Okay. What we've discovered is that whereas many previous works have attempted to control the style gun generation by... oh no, okay. I do have it. Sorry. Yeah, I have to backtrack. So in order to manipulate images using the style gun type of architecture, what we need to do is we need to decide which latent space we can manipulate, and in each latent space, what is the direction, say if we have this image and it corresponds to a certain point in this latent space, which direction should we take this point to so that we get some specific desired effect, like a smile, right? So we have to determine which latent space to use and which direction to modify the latent vector in. And what we've discovered is that even though most previous works used either the latent space, the original one, the Z, or most works actually used this one, the intermediate latent space, which is called W, and sometimes it's called W plus because it's multiplied so that we have a separate latent vector for each layer of the generation. We actually measured the amount of disentanglement that the latent representation has in each of these spaces, and we came to the conclusion that manipulating directly the style parameters, where we have one parameter for each layer, for each channel of each layer in the generator, gives us the most disentangled behavior. So basically, if we want to change just one thing in a fine-grained manner without changing anything else, that's where we should do our manipulations. And right, so that discovery was also interesting in itself, but also having done it, we have to figure out how to find these controls, because we have around 9,000 of these parameters in the style gun architecture. So which of them have a visible effect which has some kind of a semantic interpretation, right? That's the question that we were facing. So one idea that came up was the following idea. Let's consider with respect to each channel of the style parameters, like for example, layer 11, channel number 286, let's compute the gradient of that parameter with respect to the generated, the gradient of the generated image with respect to this parameter. And then we can see that some of these parameters have gradients which are focused in areas which are in good correspondence with different semantic areas of the human face, right? And this way we were able to determine, for example, that this channel controls the, has to do something with the hair. And once you do that, you can actually start playing with this channel, and then you can see, oh, that channel actually changes the hair from being brown to gray, and you can discover that another channel where the gradients happen in the eye region controls the eye gaze or opening and closing of the mouth, which is what we see here, or raising and lowering the eyebrows. And in fact, we've been able to come up with at least dozens, more than dozens, but for dozens we were able to name them, different manipulation parameters. And here you see many examples. So these are 4 different parameters that control different things in your hairstyle, 4 different parameters that control something about either the shape or the color of the mouth. You can see this one controls the lipstick, and a couple of them control opening and closing the mouth, but all in different ways actually. And these are different controls for the eyes. I like this one because it makes a subtle change and completely the ethnicity of the person is changing completely. Right. So, and notice that nothing else is changing. So that's a highly fine-grained, disentangled manipulation. And here are some examples on cars, changing the front of the car, the headlights, the grille, lots of parameters in the trained models which are trained on cars apparently deal with the front of the car. And here are some examples for bedrooms. We've already seen this one with the pillows, but there's one that just controls the length of the bed covers, and this one here controls of whether a lamp is present or not in the room. So basically, which parameters the style gun is choosing to learn, it depends, of course, on the training data that it's trained on. Basically, it latches on the main factors of variations in the data. So not all of the parameters have to do with a specific location in the image. Some of them, like gender or age, for example, affect the entire face, right? So how can we discover such parameters? So we can discover such parameters by considering small sets of examples. So for example, suppose we want to detect whether there's a parameter that controls whether or not a person is wearing a hat. So we can select, maybe 20 or 30 images of persons wearing hats. And we have a large population of images which are just randomly generated images by style gun. And then we can just compare the style vectors of this exemplar set and the general population set, and we basically, statistically, we look at which channels seem to be deviating the most from the average value over a large population. And this way we can discover many interesting controls which are not necessarily specific to a certain semantic region. Like for example here, we have the gender changing, so you can see that basically the face is changing from female looking to male looking, but nothing else is changing, right? The hairstyle is not changing, so we're not biased here towards women having long hair and vice versa. And I think I'm getting a little bit short on time, so I'll just mention that we compared this with other methods, and we've discovered that while other methods before us were able to produce similar changes, but usually their changes were less fine-grained and more entangled with other things. For example, like in this case, adding lipstick also changes the color of the face, or in some cases actually changes the identity of the person quite a bit. This is our result. So I'll skip that. This is a numeric result that shows the same. Okay, but what is this even really good for if all we can do is manipulate images which are generated by some computer model, right? So we want to be able to manipulate images which are real images, right? So what we need to do in order for that to happen is, given a real image that we want to manipulate, we want to first embed it into the GAN latent space. As you can see, this embedding is not perfect, but it manages to preserve the main characteristics of the person in most cases. I'll show later a less successful example. So this is Will Smith, for example. Once we've embedded him, we can now put some lipstick or grow a beard or make him angry or Chinese or whatever you like. There's another example. Emilia Clarke. Again, the embedding loses specific details, like this earring, for example. It gets lost, and some wrinkles and maybe some hairstyle features get lost. But overall, there is the resemblance, and then you can manipulate the image in very nice ways. Okay, so now really briefly, I want to mention something that hasn't been published yet. It's under review right now, but it's already attracting a lot of attention on nowadays when you have a new result, you put it on Twitter, right? So that's what we did. And so we have a lot of attention already on archive and on GitHub to this work. And this work basically combines the mechanism that we detected in the previous work, which is the controlling the output using the style parameters, with this new idea that just came up in January, February this year, which is the idea of contrastive text-image, language-image pre-training, or CLIP, right? So basically this is a mechanism that allows us to detect channels that control different attributes and apply them using natural language as our control, as opposed to doing some kind of analysis using gradients and the other mechanisms that I've mentioned before. So what is CLIP? CLIP is a joint embedding for text and for images, as the title says, contrastive language image pre-training. So basically we have an image encoder and we have a text encoder, and we can embed sentences and images in the same space, so we can measure the distance there and say, does CLIP think that this sentence describes well what's happening in this image, and vice versa, right? Okay, so how does that help us? Well, suppose we want to change the hair of a person from straight to curly, right? So we can embed these two sentences in the CLIP space, and that gives us direction in that space, right? Now, for each channel, for each style channel of StyleGAN, or actually we could use any other model which has controllable controls, we can generate pairs of images before and after manipulation by some delta, and we can measure the difference. We can embed these two images into the same CLIP space and measure the direction between the resulting embeddings. So then we can judge whether this direction is close enough to that direction, or maybe there's another style parameter, S prime, that has even closer direction. So basically, we actually pre-embed all the parameters S, convert them to directions in this CLIP space, and then given a query, which is given to us by two sentences, we can select quickly, very quickly, at interactive rates, which style parameters need to be changed in order to achieve this task. So let me show you some videos showing that. So I believe the sentence there says, yeah, we're just playing with different hairstyles for an embedded image of Taylor Swift. And as you can see, this is all like real-time screen capture. We can control also the magnitude of the, basically how far we go in that direction, and then the change becomes stronger or weaker. And here's another favorite. We can make Boris Johnson a little bit older by adding some wrinkles. Even if one misspells wrinkles and just writes wrinkle, apparently clip still works. That's my Chinese PhD student. I believe now it says sad face. Oh, and the opposite of sad is happy, right? And this is a more female-like version of the British Prime Minister. And again, if we go the other way, we make him more masculine. Actually, there's also a disentanglement slider that lets us determine how many different style parameters are affected. The more style parameters are affected, the more drastic the changes, right? So, the changes could be slight or more comprehensive. Now, not only people, right? I hope I have 2 more minutes to show this. Classic car. Or, you can change a family car into a sports car. Apparently, the opposite of the sports car is the minivan. Oh, and of course, nobody can, cats are all over the internet, so obviously one cannot have a paper without cats. Oh, this is a cute cat. Apparently, clip things, cute cats are characterized by the size of their eyes, and the ratio between the eyes and the... There's lots of fascinating biases in the way clip thinks about which sentences go with which images, because it's based on like 300 million pairs of images and phrases from the internet, but I mean, that's what you find on the internet. So, just to finish with one word, basically, I posed the question, is this the end of the stock photography? Maybe we're not quite there yet, but I wouldn't, I wouldn't purchase stock of stock photography companies right now if I were you, because it seems that generative models are very, very close to giving us the same amount of choice and freedom as one can do, or more than one can find on sites. And still, there's stuff to be done. GANs are not nearly as able to handle diverse data sets as we would like them to. And I've already mentioned that the inversion of real images into the GAN latent space sometimes leave room for improvement. So, for example, unusual hairstyles, and again, like earrings and things like that. Interesting things happen when you try to invert the image of Donald Trump. Suddenly you get something completely different. Oh, actually, this is a joke, but in fact, these both are inversions into the GAN space of Donald Trump and of Joe Biden. And as you can see, both of them are not quite like the original. Actually, I couldn't find the original images, but I mean, the resemblance is not so great. So with that, I can finish and take some questions. Thank you.
Thanks, Dani. And yeah, this was fascinating. I'm sure there are many questions. So while I think we have time for a short question from the audience. Anyone? While you think about that, I have a few announcements to make. Can you, microphone? Anyone? Okay, there. On the way to the question, so we'll have lunch soon. The lunch, wait, we are not finished with the questions yet. We have lunch soon. This was in the halls south of us. We'll have a poster session afterwards, and please, we will have a poll about the favorite posters. So please, when you visit them, think about them, and we'll send a poll via email. And okay, you want to ask a question?
Yes. Can you hear me? Really early on, there was the thing about converting images of like zebras to elephants, stuff like that. I noticed that the background really changed in those. Is the newer methods that you presented somehow able to change, to overcome that basically, to change the animal without changing the background?
Yeah, well, no, the background, the state-of-the-art GAN inversion methods, they are usually not able to preserve the background, because the GAN is trying to learn the subject, and usually there's a big variety of backgrounds, and neither the generator nor the discriminator can tell which backgrounds are better than others, and so like in GANs that generate, for example, images of cars, basically none of the components of the network pays much attention to the background. And at the moment, I think if you want to keep the background unchanged, you have to employ some kind of additional solution, basically to segment out the object of interest, modify that, and then superimpose it back onto the background.
Okay, we want to be on time, so let's thank Dani, and I'm sure you'll have many questions, and you'll have time now. You'll have time now during lunch and the posters to ask more questions. So as I said, lunch will be served soon. It's in the area south of here. Then on the poster session, please, think about the posters you like most, so you can vote for the best poster award that will be given on Tuesday. At 2:50, we have a group photo outside, so please come on time, unless you have a gun that can generate the group photo. And then, we don't need to put any makeup today. And we will be back here at 3 p.m. for the next session. Please be on time. We are in an international broadcasted conference, and we want to start on time for the people online. And I think that's all, right? Okay, thanks everybody. Enjoy the lunch. Thanks, Dani.